So you guys looked at hysteresis loop, correct? Now, where we use hysteresis loop, see, suppose let's say I have to make a permanent magnet. Okay, so permanent magnets, they should always have the magnetic field, correct? Now, what type of material should I use? Or let's say I want to make an electromagnet, what type of material should I use? Because always using iron is not a good thing. Okay, or see, we can also use steel, we can also use neodymium for making permanent magnets. So how do we decide what material should be used for that particular purpose? Okay, now for permanent magnets, see, think about it. If I should have a permanent magnet, it should retain the magnetic field for a very long period of time, correct? Meaning, if it should retain, what should be more? Retentivity should be more, correct? This is one point. So, one more thing. If it has to have the magnetic field, see, the opposite magnetic field, or what we call as coercivity, even that should also be very high for a permanent magnet. Okay, see, why? Because one, it should retain the magnetic field. Two, if I keep some other magnet between the two permanent magnets, that the permanent magnet should not lose its magnetic property, correct? Right? So for a permanent magnet, retentivity and coercivity should be high. Okay, so as you can see in this hysteresis loop, so retentivity and coercivity both are quite high. Okay, now steel has this type of property. Okay, that's why most of the times steel is used to make permanent magnets, especially cobalt steel. See, cobalt steel has a retentivity of about 18 into 10 to the power of 3 ampere per meter. Okay, and coercivity of almost 1 Tesla. Almost 1 Tesla. Okay, so it has very high retentivity and very high coercivity. So this is a very good material to make a permanent magnet. All right. Now for an electromagnet, see, electromagnet is what? So you switch on the current, it changes into a magnet, you switch it off, then again it should come back, it should become a metal, correct? But see, for that particular material, it should have very high retentivity, but it should have very low coercivity. Because see, suppose let's say I'm trying to make a big electromagnet, okay? So I switch on the current, okay, and then it attracts all the metal or any metal pieces. Then see, I have to transfer from this place to this place, let's say from one place to another place. Now I cannot keep on giving electricity, correct? Because it's a waste of energy. So what if I switch off the electricity? If that electromagnet can retain the magnetic field, that's much better for us, correct? Because it's more economical. So that means the retentivity should be very high, correct? So I switch on the current, it attracts all the metal, then I switch off the current. Still the electromagnet has very high retentivity, so it attracts the metal. Okay, then you move from one place to another place, and then you give the current in opposite direction. Okay, so opposite direction, then what? It should become a metal again. So that means it should have very low coercivity, correct? So this is the reason why soft iron is used to make electromagnets, because it has very high retentivity but very low coercivity. Okay, it's the same reason why even transformer cores are also made up of soft iron. All right, so what we say here is, for electromagnet and transformer core, we use soft iron because the hysteresis area, the area under the hysteresis loop, is very less. But for a permanent magnet, we use steel because the area under the hysteresis loop is quite big. Understood, right? So this is how we choose metals, okay, or any other material to make a permanent magnet or an electromagnet. All right.